All right. Welcome to United Astronomy Clubs of New Jersey. So, I see we have some people wandering down here in time for the presentation. Want to welcome you all to our location here in Jenny Jump State Park in Hope, New Jersey. Big shout out to our park people. If you're looking for a good place to camp, hike, do all sorts of fun outdoor recreational type things, do check them out. They do have cabins and sites that you could camp, and they often send people up here when they're like, well, what do we do here on a Saturday night? You come up here to the observatory. In addition, we do live stream these on YouTube and Twitch. So if you're ever sitting at home wondering, man, I'm bored, what can I do? Well, you can learn about whatever cool astronomy and science topic we happen to have that week. I moderate online chat, so I love to see you there. So again, Twitch and YouTube, and all these links are available on our website, uacnj.org. That's where you're going to find a list of all our upcoming talks, our past talks with links to our archive on YouTube, as well as information on all our member clubs, because we are a club made up of other clubs. We are a nonprofit, and we do our best to try and get our science and astronomy outreach to as many people as possible. And a lot of times it's getting you in touch with your local astronomy club, because if you don't have to drive an hour to do some astronomy, get a little plus there. Save some gas in the economy. All right. So, for all the people who are here, I'm going to give the safety briefing. It is inescapable. I will go over it later because I always see people sneaking in thinking, I can avoid it. No, you cannot. If you need to use the bathroom, that is the porta potty in the back to my left, your right. It is illuminated by red. We have remembered to turn on the red light this week, so it makes it easy to find in the dark. We also have a little museum area and gift shop. I will be manning that after the talk, mostly after, just because I can't be in two places at once. Someone who makes that technology, get in touch with me. I'd love to be able to do more things with my day. Until then, again, I'll be in there after the talk, but feel free to wander and browse. When we go to leave here, we are using our headlights. We do not like getting run over. We do not like filling out paperwork when you get run over. So let's just avoid that unnecessarily trip to the ER and all those unnecessary medical bills. We are in the U.S. I heard giggles out there. That being said, when we are wandering down, it is overcast, so it is going to get quite dark. Do keep those flashlights, or if you're using your cell phone to illuminate the ground, try and keep it pointed towards the ground, because we don't need to have anyone blinded, because someone's doing neat light rave things. Someone had a little thing like, oh, that's really neat, but now I can't see anything. And the only person who should have trouble seeing tonight is me, since I am moderating online chat. Or at least that's my hope. With that, you're not here to hear me talk. You're here to hear Paul talk about what...
I've got a hole in my pocket.
I'm like, I forgot the name of his talk. He's going to tell us all about what type of hole he has in his pocket, probably from paying bills. Anyhow, Paul has a Bachelor in Engineering and Chemical Engineering from Stevens Institute of Technology and has worked in the environmental and chemical industries. Though always interested in space and celestial objects, Paul's official start in amateur astronomy was being very uncomfortable and cold in the winter on his roof, finally getting a glimpse of the Galilean moons. From there, he was hooked, acquired a reading list that puts our reading to-do list to shame. That pile on our nightstand. Yep, just completely to shame. And with that introductory reading, he purchased his first telescope and is now an active member of Northwest Jersey Amateur Astronomers and volunteers here at United Astronomy Clubs of New Jersey. He still manages to frequently find himself cold and uncomfortable outside because, outside is outside. And with that, here he is with his talk.
Thank you, Kim. Hello, everyone. I'm Paul. Am I coming over the speaker? I can't hear myself currently. Sounds like I'm popping a little bit, so I guess I am. Yes, tonight's talk is I've got a hole in my pocket, famously said by the cartoon version of Ringo in the Yellow Submarine from United Artists and King Features. So what are we going to talk about tonight? Blue meanies? Does anyone get that joke in the age crowd that we have here? I don't think so. All right, this is a 1960s. I saw it in the 1970s when it played over broadcast TV, where Paul, John, Ringo, and George saved the day from the Blue Meanies. Here's the Blue Meanies all happy at the end because the Fab Four intervened. And of course, we need the eponymous Yellow Submarine for any of that to make sense. It does appear quite often in the movie. So famously, Ringo said, "I've got a hole in my pocket." And I thought it was excellent because it brought immediately me to the frame of mind of holes and also things that are kind of mystical and psychedelic. And so what is this talk really about? Because we're not going to spend an hour talking about the Yellow Submarine. We are going to talk about black holes. I've got a hole in my pocket, demystifying. That's the psychedelic and mystical portion of the talk, demystifying black holes. And I am a member of Northwest Jersey Amateur Astronomers. That's the member club that is a member here. I'm an observer here at UACNJ. So I'm going to fess up here. Who's got the tea on black holes? Well, not me. I'm an amateur astronomer. I'm not a professional. So this is actually a report. And it's loosely based on a video series that I watched. That video series is from the gentleman who is the expert, Professor Filipenko. Black Holes Explained. The publishing company, the learning company is The Great Courses. It was in 2009. It's a 12 half-hour lectures. And just a little bit about Professor Filipenko. He is a professor at the University of California, Berkeley, and his research focuses on supernovae, active galaxies, and at optical, ultraviolet, and near-infrared wavelengths. He tries to look for these things, as well as black holes and gamma-ray bursts, and the expansion of the universe. So listen to him, and not to me. If there are any discrepancies that, or you feel that there are any questions, look Professor Filipenko up. He is the gentleman with the expertise and knowledge. So what are we going to talk about tonight? We're going to talk about black holes. What is a black hole? Some gravity concerns, what types of black holes there are, how black holes are formed, something about the facts of black holes. You may have seen at some point recently some pictures of black holes. How does that happen? What happens if, you know, and we're going to leave that a little bit vague for just in case we have any young ears listening tonight. What's LIGO doing with black holes? Will the Large Hadron Collider do bad things with any micro black holes that it might create? We'll talk about Hawking radiation, hair, and S. little bit more about that maybe at the end there, so we can understand that better. And then finally, other things that Professor Filipenko speaks about in that are a little more ephemeral, but still, I do want to mention them, and then maybe you can look those up yourself, or look at the course to understand those things better. So first off, we're going to start off with what is a black hole. And the black hole is a concept. All right, so the black hole, and sometimes people confuse the language a little bit, so let's just start with the fact that the black hole is a concept. It is a region of space where nothing, not even light, can escape. There is an aspect of the black hole called the I'm getting ahead of myself. Who's Carl Schwarzschild? He formalized the concept of the black hole, and he calculated the radius which light could no longer escape at r equals 2gm over c squared. C squared you'll recognize as the speed of light, and g here is, in our next bullet point, is Newton's universal gravitational constant. Black holes do what they do because of their massive gravity, and which is a function of mass. The above equation can be derived as escape velocity using Newtonian physics, or from general relativity. Which is correct? And does it really matter if you can get it both ways? Well, the answer is yes. It does matter. All right, first a little bit more about what the parts of a black hole are. And I said black hole is a region of space, and people confuse sometimes some of the terminology. There is the singularity, which a lot of people think of as the black hole. I want you to get in your minds that the singularity and the black hole are describing two different things. The black hole is, or the singularity is, the mass shrunken down to a very tiny space. How big? We don't know. But that is the singularity, and people think of that as the black hole. That's not the black hole. The black hole is this entire system of things. So if you can understand a little bit more about what's happening if you think of the black hole as this system and not just as the singularity. You have a relativistic jet here that is a function of this accretion disk. And I was reminded today to make sure I told people what an accretion disk is. An accretion disk is orbiting material that is falling in and quote-unquote feeding the black hole. There's the event horizon, which Schwarzschild defined. And there's this thing here called the photon sphere, which is just above the event horizon. Not pictured in this particular diagram or picture is something else that's also very important in our understanding of black holes, or black hole companions. This is a stellar black hole. This might be something else. This is a stellar black hole that is feeding, has an accretion disk, has those relativistic jets, but is also feeding off of its companion, a binary star. So the black hole used to be another star in this star system. It's now a black hole, and it's feeding off its companion. Just double checking here. Yep. Okay. Black holes, as you approach them, are not dangerous unless you approach them too closely. They act as any other object of the same mass. So they can be exotic, but they're also mundane. Because if you were to take the sun and shrink its mass so that it forms a black hole, the Earth would not know the difference. We are not close enough to it for that black hole to affect us from a gravitational point of view. Of course, we wouldn't be particularly happy that the sun disappeared and now that there's a black hole there, we would no longer be receiving radiation that keeps us warm from the sun. However, gravitationally, we wouldn't know a difference. We would continue orbiting around that black hole and we wouldn't know. So it's mundane, but it's also incredibly exotic. We don't know what the material of the singularity is. We don't know what it's made of. It's called a singularity because our physics and math basically blow up. You get, divide by zero and infinity errors when we try to describe it. Although treated mathematically as a point source, anyone who's technical knows that that's a geometry thing that affects things more affects real life things from a mathematical point of view, that we treat it as a point source. Some experts do not believe that it's actually infinitely small like the mathematical point is. We are prevented from directly observing the singularity. And I want to just put a fine point on that. It's not that we don't have the technology to directly observe the singularity. It's that we can never directly observe the singularity. Because if we were to pass the event horizon and try to get any information or data back about something that went in, it's not going to happen. Physics actually prevents us from knowing it. So that's an important distinction. All right, so let's talk about the gravity concerns. A little bit about, what's the deal there? Why can't we use maybe Newtonian physics? So gravitational combat, Newton versus Einstein, fight. All right, Sir Isaac the Classic Newton has this to say about orbital, how you calculate orbital velocities. This is actually the escape velocity, and here is the escape velocity. And we'll talk about this. This is basically a good diagram, but I hope maybe someone can point out to me why it might be a little incorrect, but it'll still help us understand what's going on here. This is 1/2 mv squared, and this is gm, or capital M, small m over r. Does anyone recognize the two sides of that particular equation? This is kinetic energy. This is gravitational potential energy. So the escape velocity is anytime you're above, just above, when those two things are equal. That is the escape velocity, and you can escape the gravitational pull of a planet. So all you do here, the m's cancel, you bring the 2 over to the other side by multiplying both sides by 2, and you take the square root, you get v escape equals this thing here, which looks very much like Schwarzschild's, you put c in for r, and it looks very much, and you solve for r, and it looks very much like Schwarzschild's equation. So let's discuss that previous slide. If Newtonian physics were to rule the day, all we'd need to do is to, what I just said, substitute C and then solve for V, V being equal to C in the case of light. But remember, light has 0 mass, and you cannot go faster than the speed of light. So why is this incorrect? Well, little m, I just said, is equal to what? Because light has no mass. 0. So you get 0 equals 0, and you no longer have this equation. Also, this orbiting satellite can achieve this velocity by like firing onboard thrusters or something like that. However, if you are at the speed of light and you fire onboard thrusters, you are the best technician in the world and you make the best rocket ever, and it's you burn with the power of 1,000,000 suns. How much faster are you going to go? 0 faster, because you cannot go faster than the speed of light. So the way this is set up just breaks down. You just don't have it in Newtonian physics. So Albert the General Einstein, this is the other side of the fight. What did he say? He said that it isn't this mysterious gravitational attraction that happens between two massive bodies. He thinks of something different. This is an object. It doesn't have to be a black hole, but in our case it is. This is an object that is warping the fabric of space-time. So the curved paths, the orbits that you see from objects influenced by a massive object does not have to do with that invisible attraction that Newton portrays it as, but that this curve happens because space-time is actually curved and is drawing that object into the mass. So space-time is warped and the object travels along a curved path. Now, if we were to use another analogy and call our various masses a ski trail, which ones would you rather ski on? Let's call this one, the sun here, as the bunny slope. This one here looks more like a red trail. That's a pretty serious slope there. Let's call this one a double black. This is the white dwarf here. This black double diamond, black diamond, is a neutron star. And this black hole here with a singularity that just rips space at the bottom of it is the extreme trail. So you probably wouldn't want to ski that trail. And that's what's happening in a black hole. Rip space-time. The slope to get back out of here is such that even the speed of light, which is the fastest thing anything can travel, anything that doesn't have mass must travel at the speed of light. Even the speed of light cannot overcome this slope, and you are drawn inevitably into the singularity. That is Einstein's idea. So Einstein was the winner. Schwarzschild did base his calculation on Einstein's theory of relativity. There it is. There's the equation again. Solved for R instead of V. All possible paths, all possible futures lead into the black hole, even massless light. That's the universal speed limit. Nothing can travel faster than it. Einstein's the winner. Black hole, let's move on to black hole sizes and types. Black holes, these are loosely defined. There is no tremendous meaning to them, but it's the current convention. There are 5 black hole types here: stellar, supermassive, intermediate, primordial, and micro black holes. Size range, this is M, that symbol is the sun, so the mass of the sun, size range. Stellar can be up to several hundreds times our current, the size of our sun. And where can you find them? Everywhere. Anywhere there are stars. Supermassive black holes exist. There are hundreds of thousands to billions the mass of the sun. This star here indicates there is some scientists who define it differently. That's okay. It doesn't change the concept at all. In the where can you find supermassive black holes? Typically in the center of most galaxies. Intermediate black holes. There's those are from 1,000 to hundreds of thousands. They fill the gap here between stellar and intermediate, and candidates in places like the center of globular clusters. These are all in green. Evidence exists for all 3 of these. We have evidence that they exist for all 3 of them. These guys are more theoretical. Primordial can be from micro to intermediate, at least from the source that I read. NASA was my source for that particular piece of information. None have been found of the primordial black holes. They occurred just after the Big Bang. And it's interesting. We can talk a little bit if you have questions about it, what a primordial black hole might be and why the search for them is interesting. And then micro black holes, which some have theorized. Atomic to asteroid in size, they're the original mass. And then none of these have been found, and they might be created by where we find them where there are high energy particle reactions. How are black holes formed? Well, we're a little less certain about some of these that we were more certain about on the previous slide. We again have the 5 types of black holes. We have size ranges that are the same, because those are just categorically the same. But how do they form? Well, the stellar black holes form from a stellar remnant. Supermassive black holes, we know they accrete mass and energy. And the intermediate black holes, yeah, well, we know they also accrete mass and energy, and that's how they get bigger and stuff. But where did they come from? That is still a mystery. We have these primordial black holes, which they were formed during the Big Bang through gravity and phase fluctuations during the Big Bang when it unfolded. And these micro black holes, again, they are high energy particle reactions, and I did throw in there, but they evaporate quickly, so can be extraordinarily hard to detect. But again, here's the big difference that where the supermassive and intermediate black holes actually originated from, a little bit of a mystery still. So let's talk about how stellar black holes are formed. And this is from a presentation that I do on stars. This is what besides fusion stops star collapse. So a star, when it exists, is in what we call I'm losing the vocabulary. It's in equilibrium. It is in, I will think of it. It is equilibrium that you have the force of gravity pulling it in and the force of the fusion pushing it out. So gravity's pulling it in, fusion's pulling it out. Those two forces are in balance, and the star is hopefully stable. So when the fusion, the star starts running out of material, or we hit iron.
Hydrostatic.
Thank you. Hydrostatic pressure. When the hydrostatic pressure gets disrupted,
Equilibrium, not pressure.
hydrostatic equilibrium gets disrupted, and I'm going to move away from the terminology because I'm having a hard time with it right now. But when the electron, when it's interrupted by the star losing fuel, or when the star core reaches iron, which actually requires more energy to create than is released, then the star will start collapsing. And so what stops the star from collapsing and make it become a stellar remnant? The electron degeneracy holds up white dwarfs. So it's a state of matter where particles with like quantum values have to stay separate. The free electrons in such a star order themselves, and when I say order themselves from a quantum point of view. It's actually a mess of very energetic particles, and provide that electron degeneracy provides a back pressure to resist gravity and prevent the star from collapsing. If electron degeneracy isn't sufficient, in other words, the solar mass is big enough, it's just under 1.5 solar masses, the star will continue to collapse because the electron degeneracy doesn't provide enough resisting force anymore, so that more massive, that bigger gravity star continues to collapse. Neutron degeneracy then becomes our hope to prevent collapse. Neutron degeneracy holds up neutron stars exactly like electron degeneracy does. It's that Pauli exclusion principle again, and it's still particles prevented from occupying like states, and they have to stay away from each other. And the reason why the neutron stars get a little bit of a kick besides that degeneracy pressure is that they also get an assist from the strong force to resist the further collapse of the star. So they can exist for larger masses, between 1.5 and 3 solar masses. That's the mass of the remnant, not necessarily the mass of the entirety of the previous star. Beyond those two opposing forces, in other words, when the star gets so massive that neither of those pressures work to prevent the star from collapsing, I don't have anything else to suggest, and neither does the universe. The star will continue to collapse. That's when we get a stellar black hole. Here is a supernova remnant, W49b. This is the suggestion for this slide came from my previous presentation. However, this is a new picture. This is, in my previous two pictures, I had the Ring Nebula and the Crab Nebula, and they had respectively a white dwarf and a neutron star in their center. This, we can't find anything in the center of that. That might be a black hole. We can't find it, but there's something there. That's not great corroborating evidence, but that is, hey, we might suspect there's a black hole in there. All right, here's models acting out how intermediate and supermassive black holes accrete energy and matter. Now, I don't remember accreting's consuming. These guys are professionals. I can't speak to what their actual process is. I don't know whether they were thinking about black holes. But these sandwiches, if they were thinking about black holes, would contain things like interstellar gas, star systems, stellar remnants, including neutron stars, white dwarfs, or even other black holes, and even two supermassive black holes. These actors are portraying accreting matter. All right, let's talk about some of the facts. What evidence, what real evidence do we have that black holes really exist? Well, we just talked about there's something there, but we can't see it. And with that asterisk there, a detective might say that needs corroborating evidence. That's true. Well, we'll talk about an X-ray source from an accretion disk of material stolen from a companion. And let's see here if this works. We just talked about that, right? We are, sorry, let me go back here because I think I hit the wrong thing. Hold on. Let me go back to here. Something's there, but we kind of X-ray source from an accretion disk of material stolen from a companion is not that slide. It's this one. Sorry about that. And I got it wrong again. So we're going to G, and I'm going to search for it manually. That's going to be faster than me trying to be fancy. And here it is. All right, so that's this picture that we showed. That's why this is important. This companion, as thinking of it as part of the system, is actually, we can't believe that it's a black hole unless we have some sort of corroborating evidence, right? That doesn't mean that black holes don't exist that are on their own and don't have a companion. They do, most likely. It's just that we don't have evidence for them. We have maybe that something's there, but here we actually have evidence. There's X-rays coming from this relativistic jet coming out of the black hole. That relativistic jet, by the way, is a feature of the accretion. It is not actually coming out of the singularity, which of course nothing can come out of. It's actually coming out of the system, the accretion of the material from the companion star. All right, I'm abandoning the shortcuts and going back to this method here, and here we go. All right, star wobble of a companion. We'll get to that one in a minute. The missing afterglow. Well, I can go back real fast this way and show you that again. A missing companion in a remnant. I mean, the missing afterglow in a remnant. We're just not seeing the neutron, the signature of a neutron star in that remnant. And here we go for the star wobble. It's a nice animated GIF or GIF, however you want to call it. So here is, let's say, this is denoting where the black hole is, and this is its companion. And you are seeing this guy here wobble. So what's happening here? This is spectra that we've taken from this companion, and that spectra is red shifting and then blue shifting. And if this is the black hole and that's the companion, this is actually reversed, red shifting and blue shifting, because I think it was really meant to describe this star, but you still get the idea. When this guy is moving away from us, it's the Doppler effect, it gets red shifted. When it's moving towards us, it's blue shifted. It's that same material, but it's shifted towards the blue side of the spectrum as this wobbles back and forth. You can tell it's moving towards us. So blue is towards, red is away. and that is a star wobble and what it would look like. Gamma ray bursts. So this is a supernova, and this is a relativistic jet that is releasing lots of energy. A gamma ray burst, which would be more evidence of a black hole, a long duration gamma ray burst, which would be over 2 seconds to hundreds of seconds, maybe, denotes a stellar collapse. And the reason why it's longer is there's just a lot more material there. With a star, more loose material gets pushed off into space. This relativistic jet excites it, very energetic, and makes it last a longer time. A short duration gamma ray burst, less than 2 seconds, might be a neutron black hole, or a neutron star black hole, or a neutron star collision, which would still have some material being pushed off into space, but not as much loose material as a star. So therefore, it would last not quite as long. Quasars. Now this is interesting here. Let's, I have to use G here and go back to what a quasar is. A quasar is something that does look like this, which is a supermassive black hole in the center of a galaxy. You can see the galaxy back here a little bit, so I'm assuming this is a supermassive black hole. But what's happening is a gamma ray burst is material coming from a relativistic jet happening at the most extreme energies. Gamma rays is really energetic light hitting us. And what that is a supermassive black hole feeding. We find these gamma ray bursts coming from the center of galaxies. Excuse me, the quasars coming from the center of galaxies. And going back to this, oops. Sorry about that. Trying again here from the current slide. G. And coming down to here, what we find is an extinction of these. What's happening is we're here on this side. This is where we are. This is the cosmic time. This is how far away we can look into the universe, because a light year means that light took a year for it to get to us. So if we're looking at things that are billions of light years away, we're looking back in time that many billions of years. And what we find with these quasars is that they have a density a certain amount of time backwards, and then they start disappearing and are gone after a certain period of time in our universe's history, or the same thing as they get closer to us, because we're no longer looking so far back in time. And so what that means is what? That material was widely available for the quasars to munch on, but it disappeared over time. And so the black holes became more and more quiescent still, because they are just not eating much, if anything, anymore. And so they are giving off less and less energy. These quasars, by the way, outshine entire galaxies, have the power of trillion suns, and they shine brightly in all wavelengths. And the other thing that happens is that there's this ramping off period where quasars are no longer considered quasars, and they are considered by astronomers they're called active galaxies at that point. Here's another line of evidence, spectral broadening. Here is a supermassive black hole. It has this accretion disk and other material around it, but it has this accretion disk. We can look at the spectra coming from the black hole, this light that this accretion disk is giving off, and we see this split here. And again, just like in the case of an orbital companion, we note that the redshift is material moving away from us, and that's what causes this split, this peak on one side of the region to be redshifted, and then material on the other side as it orbits the black hole be shifted in the blue side, so you can get this peak split. So this spectral broadening. It's the same material. Some of it just got shifted to the red, and the same got shifted to the blue on the other side of the rotation. That's kind of cool. Here's the actual data, real spectral broadening data, and we just think that there are very knowledgeable, very scientific people who can analyze these graphs and make sense of them, because it is certainly a lot more complex than the example we use to understand the concept. But there's real data. So we have evidence. We have a theory. We understand the system in concept. We have evidence, and that evidence consists of those graphs and those shifts and things. So what about these pictures of a black hole? Is that real? And the answer is yes, because now we can take those concepts and understand that we have the evidence, and we can say to ourselves, especially to people who might doubt, what are we seeing here? That isn't the singularity, is it? That's the black hole system. This shadow here is part of the system also, but this is the accretion material around the black hole. It's the system. So this is the black hole. It is the system. It's just not the singularity. So if people say, well, how do we have a picture of it if light cannot escape a black hole? Well, we have a picture of the system. We don't have a picture of the singularity. We can't have a picture of the singularity. This is Messier 87. Messier 87 star, excuse me. It's taken by the Event Horizon Telescope. It has a high frequency. It's using high frequency radio interferometry in this system, this galaxy. This central supermassive black hole is in Virgo. It's 53.5 million light years away. It's in the Virgo cluster. It is the dominant galaxy in our entire cluster. It has the mass of 65 billion suns, and it's 24 billion miles across. That sounds like it's really big, right? It's actually only 4/1000ths of a light year. But it's a lot of miles. It's 24 billion miles across. This is Sagittarius A. It's another picture of a black hole. This was also taken by the Event Horizon Telescope, but they invited other collaborating telescopes for a wider field of view, so you can get a better appreciation of the area that this black hole was taken of. It was also, this was released in 2002, but the data was also taken in 2017, like this data here. This one is 27,000 light years away and 4.3 million suns. Does anyone in the audience recognize Sagittarius A star, where this supermassive black hole might be located? You got, if you know one galaxy, you got to guess it. Andromeda, close, about 2 million light years away. The Milky Way, that's our supermassive black hole. That's our supermassive black hole. So we have pictures. We have real pictures of a black hole system, not the singularity. We can't have a picture of the singularity. But we have real pictures of a black hole system. Black holes. Awesome. Wait a minute. We don't have just pictures. Look right here. See that thing pulsing right in the center there? Look at those stars whip around. That must be a heavy thing that those stars are whipping around. And it's pulsing with brightness. It isn't bright all the time. It just pulses with brightness. Look, that's material off of that star that passed really close, getting accreted by a central black hole. Ladies and gentlemen, we don't have just pictures of black holes. We have video. That's taken by the Very Large Telescope in Chile, and that is an ESO-MPE collaboration. Oh. What happens if you know? And I don't know that we have too many young people here. However, we are, little ones, but we're still going to be careful with our language. What happens if, we throw an object into a rock, into a black hole? In the case of stellar black holes, spaghettification due to extreme tidal forces will happen. The rock, say it's this big, will experience as that black hole, which is a point source, as you get closer and closer and closer, that object gets closer to the black hole, different sides of that rock, even though it's relatively small, will feel different forces on different aspects of the rock, the different sides, the different parts of the rock. And so the rock will be pulled and spaghettified, and it will be torn apart because those tidal forces will just rip it apart. The sun pulls on our liquid on our planet and makes tides. Just imagine a black hole with all its mass being in a tiny, tiny little space, all that, the different directions, the extreme bending of space-time will rip that rock apart in a process called spaghettification. In the case of supermassive black holes, you can actually pass the event horizon and not be close enough to the singularity yet, where where space-time is quite yet that warped. You won't be able to get away from it because the mass is still pulling you in, but spaghettification doesn't necessarily happen. You'll get pancaked instead. Your rock will get pancaked instead. Maybe if there happens to be accreting matter, it would be a bad day for the rock if it comes into contact with any highly energetic orbiting accreting matter. And finally, the rock will experience time dilation. Matter from objects in the black hole gravity fields will appear to slow down from an outside observer and eventually freeze in time at the event horizon. And they will just get dimmer and dimmer and dimmer and dimmer ad infinitum. So that's what happens if we drop a rock into a black hole. Now we swap the rock for a magic camera, which we can extract data from after the fact. And here is a physics model of what happens to that magic camera as it falls into a black hole's event horizon. That's saying, have you ever wondered what it's like to be a camera and fall into a black hole? Here comes the black hole, and look what it's doing to the universe already. It's gravitational lensing the stuff around. See it moving now as you get closer? It's bending all that light around. That's the light ripping around the accretion disk, and here's the light ripping around that black hole. It's actually orbiting the black hole. Now you can see the entire universe behind you and in front of you and everywhere, because the light is all orbiting, being distorted around the black hole. Then the camera falls in and becomes part of the black hole. Thank you, NASA, for putting that together. Yep, there we go. Here's, oh, by the way, if you want to see these, if you look, where is it? There it is. If you look up Sagittarius A star and very large telescope Chile with ESO MPE as your keywords, you'll find it if you want to look at that yourselves. And here, if you want to look on the NASA website or on YouTube, you can go back to my video that I'm making right now, pick up these hyperlinks and go there. So what is LIGO doing with black holes? And we're reaching the last couple minutes, so I'm going to fly through these. What is LIGO? It's the Laser Interferometer Gravitational Wave Observatory from Caltech and MIT. It detects gravitational waves from those mergers, those collisions that we talked about. They are located in Hanford, Washington, one unit in Hanford, Washington, the other in Livingston, Louisiana. The first detection of a collision, it was between two neutron stars, happened in 2017. So far, it has detected 83 black hole mergers, 2 neutron star mergers, 3 neutron star black hole mergers, and 2 mystery mergers. And scientists love mystery. Some people think that you have to explain everything in order for it to make sense. Nope, that's just new science. Can't wait to dig, for scientists, I bet, can't wait to dig their hands into that and figure out what's going on there. Here's the detectors. They're two, that's 4 kilometers, 2 4-kilometer tubes at right angles to each other. They detect, they put lasers on it to detect the length of those 4-kilometer, because when gravitational waves happen, they'll change the length slightly. How slightly? These things are so sensitive that you can move them by the width of a proton in the middle of an atom and detect the length, detect the change. So pretty sensitive instruments. This is what's happening as these things get close to each other and orbit each other. They disturb in a wave-like pattern space-time, just like Einstein said, and they are detecting these waves coming from these events. 83 black hole collisions. So that's just more evidence. Another thing talked about, will the LHC do bad things with micro black holes? The Large Hadron Collider is the LHC. It's run by CERN, which is the European Council of Nuclear Research. CERN. That's why it's CERN, and why it's a Romance language, so the adjective comes after the noun. It's based in Marin, Switzerland, which is a suburb of Geneva. It's on the border with France. It's the world's largest and most powerful particle accelerator. It's conducting multiple particle physics experiments. It's 17 miles long. It's buried about 50 to 175 meters underground, depending upon where you're standing over it. And it directs two beams of protons accelerated to 99.9999991% of the speed of light to collide with each other. And it has a nominal energy of 13 tera electronvolts. And it is electron volts. And it is on July 4th, 2012. You might remember it announced the discovery of the Higgs boson, a Higgs-like particle. I thought this map was interesting because this is an instrument doing science experiments, and you have to put it on a map. And not only do you have to put it on map, this isn't the Large Hadron Collider. This bigger circle that you don't see all of is the Large Hadron Collider. This is the collider that is feeding the Large Hadron Collider. So it's big. It's kind of cool. I thought this one also was interesting, because here's a picture of the actual Large Hadron Collider path where the particles are being accelerated, and we're talking about creating micro black holes and possibly doing bad things to the entirety of the planet. And here you are, some guy, poor guy, here's the klaxon goes off. He has to run half a mile to get to a fire extinguisher and do what? To save the planet. So no, he actually stops halfway and scratches his head and says, "What am I running for?" According to from CERN itself, according to the well-established properties of gravity described by Einstein's relativity, it is impossible for microscopic black holes to be produced at the LHC. So that's CERN, but they're CERN. So what does CERN and also Professor Filipenko say about micro black holes? Micro black holes would evaporate in tiny fractions of a second after they form. Even with a factor of safety of many magnitudes, a micro black hole that is somehow stable would accrete matter at such a small rate we wouldn't have to be concerned for the expected lifetime of the planet. So even with a many 10 times order of magnitude is, of course, 10 times. So many orders of magnitude, thousands or hundreds of thousands of times the safety factor. We don't have to be concerned because they just don't eat fast enough for it to make a difference. And I did say something here that's interesting, right? Wait, what? Did you say did you say black holes evaporate? They do. Hawking radiation. Hair and S. What's that? Here's a Hawking radiation. Here's what Stephen Hawking proposed. You get fluctuations, quantum fluctuations, they are called, in space. The universe is nice, borrows some energy to these quantum fluctuations. A particle and antiparticle pair are just created out of that energy that the universe borrowed, lent to this particle pair. However, this is a particle-antiparticle pair. So they see each other, are attracted to each other, and immediately destroy themselves. And that happens all the time everywhere. That's just part of particle physics. So the universe gave energy, they are created, and they are immediately destroyed. Quantum fluctuations. But if they happen at the event horizon, or right near, or right on the event horizon, one of the pair can fall into the black hole, releasing the other particle. That is Hawking radiation. So we talked about creating it in this quantum fluctuation. The energy gets borrowed from the universe. Well, in this case, because one part of the particle-antiparticle pair fell into the black hole, where do you think the energy comes from? The black hole. And so all black holes, if they stop feeding, will eventually evaporate in this manner. But it takes a long time, trillions of years, a lot longer than the universe has existed so far. What does hair have to do with it? John Archibald Wheeler is credited with the phrase, black holes have no hair. It means black holes only have the observable properties of mass, spin, and charge. There's no detail. It has no hair. It has a bald face. It's just those three things. That's all you can know about a black hole looking at it from the outside. They are the ultimate expressions of entropy. Entropy is what S is. The infinite states of matter and energy that went into that black hole are reduced to a frighteningly homogeneous blend of stuff. That is the ultimate expression of entropy. You randomized everything. All the structure. Is that gone? Is that information, properties of the stuff falling into the black hole, truly lost if it is being evaporated by Hawking radiation? Maybe not. There is a proposed hologram layer of a Planck length. That's a very tiny, very, very tiny, very tiny length above the event horizon where information is retained. This has implications about how we perceive information in the real world. And it's called the holographic principle. It has to do with the dependence and interrelation of properties and the understanding of the underlying physics of the universe. It has to do with how much information is actually needed to define something physically. And are we completely independent in our understanding and description of physics the way we know it now? It turns out this principle has implications that maybe we don't understand it quite as well as we think we do. All right, and finally, extremals, white holes, and other dimensions. Extremals are when physicists play with the general relativity equations and they put in impossible or nearly impossible or maybe not so impossible extreme versions of a black hole. It's like the black hole has no spin, or it has an extremely high spin, or it has no charge, or it has an extremely high charge. It's a theoretical physicist's analog of let's open this thing up and see what this puppy can do. All right, and what does that do for physicists? They don't do it just for kicks and giggles. They're binding a problem to better understand it. They're understanding its boundaries to better understand it. White holes. Dr. Filipenko also discussed white holes, theorized the other end of a black hole. Are they possible? Could they be stable? Could something potentially travel through them? And then finally, what are the implications if micro black holes are actually ever detected? Would their fluctuations of gravity imply other dimensions? And just to get a sense, it's not other dimensions. We're talking about other dimensions in the XYZ sense, not in the spooky another realm sense portrayed in like the Twilight Zone. These are high concept theoretical physics, but don't disregard their importance. It's like when, say, all of us watch a world class chef on a TV program. I may not ever have that skill, but it certainly helps me understand home cooking better and ups my own game. So this highly esoteric theoretical stuff is important in our overall understanding of the universe. I highly recommend Black Holes Explained. I urge you all to join an astronomy club, and that's it for my presentation. Stay safe, everyone.
All right. Thank you, Paul, for another great presentation. Thank you for joining us. So we are going to be doing a question and answer session. I know online chat had a number of questions. I'm sure you guys did too. But before we get into that, there's the safety briefing because I think some people snuck in. I'm not sure. I'm night blind during and immediately after the presentation because I've been looking at a screen. So, safety briefing. If you need to use the restroom, that is the porta potty in the back to my left, your right. It is illuminated by red for ease of seeing. We also have a little museum and gift shop area that you can feel free to check out. I will be manning the gift shop after we do the question and answer session. It looks like we have one of our volunteers has an observatory open, looking at the sky. What we are observing right now is clouds. So while I don't think we can get any objects through a telescope, you can at least afterwards go and check out what he may be doing and what the inside of one of our observatories does look like. When we go to leave, do use your headlights. We like you being able to see where you are driving so we don't get run over or you don't get, and so people can see you coming. Especially since now we have electric vehicles that make almost no noise. They kind of jump out at you when you're not paying attention. So headlights, very important. That being said, as we're wandering around, because it is quite dark since it is, again, clouded, do keep those flashlights and other lighting devices, try and keep them pointed towards the ground. We don't need people accidentally being blinded when we can avoid it. With that, so question and answer session for the people here. Like I said, I'm slightly night blind, so my vision's like a T-Rex. If you don't move, I cannot see you. You're just kind of shapeless, shapes in the void of darkness. So what you're going to do is raise your hand and wave it about like you just don't care. And keep your hand up until I come to you with the microphone. Because otherwise, again, I lose you in the dark.
And Kim, may I mention, as a member of the board, I'll take it upon myself and not spare Kim from having to mention this, but we are a volunteer organization. Everyone here is a volunteer. You can imagine that our budget is very small. So if you found any parts of our program, visiting the telescope or this talk, at least acceptable, if not excellent, then please, if you could donate something, it does help us keep the lights on here. So we certainly appreciate anything you can give.
Also, if you want a free way to support us, also click those like and subscribe buttons and follow buttons on like YouTube and Twitch. Follow us on our Facebook. Let us know we're doing a good job. If you feel like donating, especially if you're online, since you physically can't get here, if you're at home on your computer. We also, on our website, uacnj.org, have links to like our Patreon or other ways to donate. So, what was I saying? Oh, online chat, you have it easy. Just type your questions in chat. So, I'm going to start out with our first online question. This one you'll find funny. Paul has done a number of talks. Do you keep him chained up in the basement there, just churning these out?
uh, I actually quote unquote enjoy. It's a labor of love, one would say, that I learn by putting these presentations together, obviously, and it is my chosen hobby, and I appreciate doing it. They are a bit of work, I will say that, but I learn and benefit from them, and hopefully you all, including our home audience, find them enjoyable and helpful also.
We don't keep him physically chained up. We just elect him to board positions. I heard a few chuckles out there, so some people know the feeling very acutely, apparently. Right, questions out here. All right.
I guess it's a double question because maybe in order to ask my question, I need to first understand if I understood the overall Hawking radiation correctly and how black holes evaporate. So if I got it right, it's basically that particles of matters and antimatters, I mean, there's an imbalance and the black hole is sucking in some particles, meaning it's releasing the other particles, right? And that basically release energy out of the black hole, and that's how it evaporates.
It's not releasing the energy as the black hole per se. What is happening is that I guess you can think of it like that, but the energy for the creation of that quantum fluctuation had to come from somewhere, and because that particle fell in, it's coming from the black hole as opposed to the universe as at large.
Okay.
So that's why so nothing is getting released from that singularity. It's just some of that energy is getting pulled out of it.
All right.
From that fluctuation. I am not a theoretical physicist, so I don't have a clear understanding of its mechanism either.
It's certainly clearer than mine, so thanks for that. But so that means that this phenomenon is still completely imbalanced by all of the matter coming into the singularity?
That is very correct. If that black hole's eating, it can eat far faster than this Hawking radiation can, except for it's very size dependent. So if you're talking about a stellar, intermediate, or supermassive black hole, any accretion happening on one of those things, it will far outweigh. However, micro black holes, mini black holes, are small enough. The smaller radius makes them actually evaporate faster, and so they can't eat fast enough to stay around, and they're unstable and will evaporate almost immediately.
Thank you.
Mm-hmm.
All right. Honestly, it kind of sounds like, and for the people who have small children, you as an adult can eat an amazing amount of stuff, but a small baby can only eat so much before it goes bleh.
That's
and it can only eat so fast.
That's a somewhat gross, but yes, apt analogy. I like it.
Hey, that's kind of what I got out of it. And sometimes you need the analogies. All right, so our next online question. If you had a long enough rope to put one end in the black hole, like you're in the black hole, Paul, you have your end of the rope.
Okay.
And you're past the point of no return, and the other end of the rope is a safe distance away where you would not be at risk for being pulled in. So I have the other end and I'm far enough away. Because you have that end of the rope, would I get pulled into the black hole?
Okay, so I'm in the black hole.
You are in the black hole,
holding onto a rope.
Yes, and I have the other end of the
I highly suggest you let go of your end of the rope. Real black holes don't just sit there statically; they're spinning. Frame dragging is happening, so space-time is not only warped but it's also the black hole's also most likely a real black hole is most likely spinning. So everything's getting tangled, everything's in orbit, space itself is going around the black hole. That's frame dragging. So that scenario, like I said, it's all going to get wrapped up. Everything's going to get pulled in, and I suggest you let go of your end of the rope.
Cut the cord, save yourself.
Indeed.
All right, another question out here. All right.
So those two pictures of the black hole, Sagittarius A star, seemed quite symmetrical, and Messier 87 seemed kind of offset. Is there another black hole in the neighborhood of Messier 87 that's kind of pulling that material over?
That's a great question. And what's happening there is, remember, we're taking a picture not of the singularity, but of the black hole system. So the accretion disk is not necessarily symmetrical. It's stuff that is orbiting the black hole, and more of it can be on one, just like the planets can all be on one side of the sun at a time, depending upon how fast they're all going around and whether they catch up to each other or not. Just like all the planets around our sun can be on the, they don't have to be equally spread throughout our solar system. The same thing with the accretion disk is it doesn't necessarily have to be itself symmetric, and nor any of the other highly energetic material around the black hole, and therefore it doesn't have to be symmetrical, and that's what's happening. So it's not symmetric because the accretion disk is not necessarily a perfect circle around the black hole.
All right. So our next online question, why do all/most of the equations that include the speed of light always square it? An example that Jeff gave was E equals mc squared.
Yeah, that's a good question, and that has to do with when I talked about point source, mathematically point source. Things that are spherical tend to have fluxes, tend to have influence in a 3D sphere that one assumes around the object. Things that are point sources vary with the square of, for instance, in this case, r, the distance the distance or the velocity. So a flux in a spherical or point source geometry will have squares associated with the geometry. That's where so a lot of mathematics and stuff like that, you'll find out that, oh, this important property, this gravity, only has gravity constant or mass only has a somewhat small influence on the overall equation, where the distance has a tremendous influence on it because it's squared because of geometry, not because of the actual properties of the object. So geometry is extremely important in physics.
All right. Is there another question out here? Since I only hear crickets, and that's okay because we are in a state park, so we are in their home. I'd actually be more alarmed if I didn't hear any crickets at all.
Might have been a black hole that got them or something.
I'm going to move on to our next online question. And if you guys have any questions, like I said, raise your hand and wave it about like you just don't care. Right. Our next question was, could you detonate something inside a black hole and destroy it?
No. Energy, all energy, just becomes additional mass added to the black hole. So even if you were able to detonate something in a black hole, anything that you would put in that would be a bomb would, of course, get destroyed by the black hole as it falls into the singularity. Anything that you could get there, hypothetically, and were actually to light off and turn into energy, the energy itself would be absorbed by the black hole, turned into mass to add to the black hole.
And this was probably a follow up to that question. Could a black hole eat enough stuff to become not a black hole?
As I don't know, but what was the uh, number on excuse me, on M87 star? It was 6 billion suns. That's a lot of suns. That's a hefty black hole. I don't think that there is an upper limit on matter falling into a black hole. I think actually, if I remember correctly, it was theorized that instead of, now we know that the dark energy is causing the universe to travel further and further apart, faster and faster. There was one point where physicists were debating whether or not gravity would eventually overcome all the initial energy of the Big Bang and collapse the entire universe back into a singularity. So I don't think that they think that there is an upper limit to the mass of a black hole.
Ooh, we got another question out here.
Thanks. Can you elaborate a little bit on the theoretical black holes? You mentioned there's two types. I think the
Primordial and,
primordial,
and
the
mini
atomic
or
one
micro.
or the minimal one. You said the primordial had a certain interest, no?
What's interesting about primordial black holes is how we're looking to find them. And we're looking, if you know proof by induction is not where we prove X, but we prove that anything other than X is impossible, right? So that's proof by induction. Well, it's similar thinking, not quite, but similar thinking, how we're looking for, theoretical physicists think we can look for primordial black holes, is that we're looking for that final, as I said, as mass, the mass of a black hole decreases and decreases, the smaller it gets, actually the faster it evaporates, right? The micro black holes disappear very quickly because all of a sudden a lot of Hawking radiation is given off by it. It is inversely proportional to its mass, the Hawking radiation given off. So what they're looking for is not the primordial black holes, but the disappearance of a primordial black hole by it eventually evaporating and all of a sudden all this Hawking radiation given off because it evaporated. We haven't found it yet. We as a, not that I'm looking for it, we as a species. And someone began to have another question.
Okay. I'm like, I can't figure out where you are.
Is there a defined size to the black hole for stability where the Hawking radiation isn't putting out energy faster than it's consuming? Is there like a
That's
minimum?
a great question. There probably is, and I unfortunately do not know that size. I do not know it.
All right. So I know I have two more online questions. I'm sorry, online chat. My computer and my phone decided that internet was just not a thing they were having. So I have the two last questions for you guys memorized. If you were to fall into a black hole and you were to become spaghettified, does that mean I can finally be supermodel thin with legs for days?
You would certainly not be able to enjoy being supermodel thin, because impact to the singularity is imminent.
It was funny.
That's a very destructive process. It's not like you get drawn out and you're still, you look like Beaker from the Muppet Show, right? You are. That's not what happens. You don't still exist. You get torn apart in that process. Excuse me. A rock thrown in gets torn apart in the spaghettification process.
Yes. Yet another unrealistic beauty standard to live up to.
Indeed.
All right, and the second one, which I have memorized, and I'm gonna try and get chat back. But if you do have a question and I don't see it, do once the live stream ends, do comment it. I still check comments on our YouTube archive often enough, and I will try and get those answers for you later if I cannot get the internet back. The second was, is there a black hole in the center of every galaxy?
No, because of course we live in the real world or the real universe, and the universe is infinitely complex, and there are things that are happening in it all the time that we don't understand why. But yes, by and large, the vast majority of galaxies have these huge supermassive black holes, but scientists, astrophysicists have identified some galaxies that they don't think they have black holes in. But remember that these measurements are extremely complex. Between us and millions or billions of light years away, there's a lot of stuff in between. You got to take that into account. It may be further than we think it is. It may be closer than we think it is. It may be XY interference is happening. It may be Y interference is happening. So these things need to be sussed out over time, and there is always some uncertainty related to these measurements. But there are candidates of galaxies. I don't know whether it's been confirmed, but there definitely are candidates of galaxies that the scientists do not believe there are supermassive black holes in the center of.
All right, any last minute questions out here? Oh, we got one more.
When you're talking about fusion earlier with a star, taking hydrogen, making helium,
Yep.
producing energy, and eventually you said when it gets to iron, the energy is created is less than energy
Released.
forming it.
Right.
So is that what's happening in a black hole? I mean, is there any theory on that?
They don't know because we can't know. We don't know what is actually in a black hole. It is not. If it is producing energy, maybe it is. We can't say it's not, right? It's not releasing it to the universe, except maybe through this process that Professor Hawking has identified. However, we just don't see that that energy isn't coming out, so we don't know that that's happening. We don't know what that material is. We don't have the physics to describe it, so we can't say that it is or is not producing energy. We do know that it's accreting energy from the universe. We can't say beyond the event horizon what is happening. So that the answer isn't yes, no. The answer isn't even really maybe this, maybe that. The answer really is we don't know.
Right, and it looks like we got this one, and then we'll wrap this up.
Maybe a simplified way of asking this, but so if you said that black holes have an effect on space-time continuum and they distort it, how much can you trust a light year? Because it's a space, but it's also a way to measure time, right? It's so and how much can you trust your measurement? Like how
beyond the event horizon, you cannot, because we can't know what's going on in there. Our laws of physics break down at the singularity. We can't know. That's why the video stopped at the singularity as the camera fell in. It's just, I can't know. However, for any region of space where our physics calculations still hold up, we can certainly predict the physics, given general relativity and other sophisticated understandings of the physics. We can understand and predict and even produce numerical and even image models of what is happening. So we can be certain to a certain point, and then the best thing we can say is, as I said, it isn't maybe this, maybe that. Scientists might speculate, but they'll never say that they really know, or that it's really, they'll always say we don't know, because we can't predict it. We're actually prevented from knowing what's happening.
Sorry, I got distracted by the bug. So thank you all for your questions. Like I said, if you have any more, feel free to put them in the comment section of our YouTube archive, or you can also go into our Discord channel or on our social media. We have Facebook, we have Instagram, Discord again. Go ask your questions in there. If I can't answer it, or if it's a question directed for like Paul or like Dan, because you went back and watched one of Dan's talks, I will ask the questions of them, much to their dismay, perhaps, but too bad they signed up. Ha ha ha. And I will try and get you those answers to the best of my ability. All right, so I want to thank you all for joining us here and online. And with that, everyone have a safe night. And until next time, next Saturday, when we'll be back here, clear skies and good seeing.
Thank you, everyone. Good night.